Good morning, everyone. Welcome to our call this morning. I hope you enjoyed the little video, and if you were on with us last week when we started this series on plastics, you've seen this video already. So we like those little videos. They illustrate the complexity and the problematics that people face every day very nicely, and that's why we like to play them. If for some reason you're just joining us and you missed it, then we normally play them again at the end. So stick around if you want to see it again. So again, welcome to our call today, which is a mouthful. It is how to analyze mold cooling, line layouts, and predict molding part warpage using SOLIDWORKS plastic. So not necessarily a market-driven or marketing-driven title, but more of a functionality-driven title, which is what we were going for to make sure you understood what we were going to present today. My name is Joelle Guénette, and I am the Territory Sales Manager for Eastern Canada. And I cover from Ontario to the Maritimes. If you're joining us from the U.S., from the Eastern area or anywhere else, we welcome you on the call as well, of course. I have with me the privilege of having Sashi Simbayatha. Sorry, there you go. Is exactly what I thought I would do with your name, which is why I normally just say Sashi. Sidham Baram, and I'm sure I will get to say that very nicely one day. But you know what? Most people have trouble with my name since it's French. But I also have Michel Cloutier on the line with us. Michel held the conference last week, the webinar. So if you were on with us to learn more about plastics from a parts design, then you got a lot of information last week. The webinar, which is recorded, so you can always reference back to it if you missed it, and get some more information that you can share with others as well if you want. So before I introduce Sashi, just a few things of housekeeping. We do have a handout, so if you look at your panel on your right-hand side for GoToWebinar, there's a handout that you can download for yourself and look at any time. And in the chat area, there's type message here where you can type any questions that you may have as we go. Please don't hesitate. We do these so that you get information that you need for the work you do on a daily basis, and we want to make sure that we're addressing things that are specific to you. So please don't hesitate and use that panel. All right. So back to introducing Sashi. As I said, we have the privilege of having him with us today. Sashi is a mechanical engineer. He has a master's degree in it, and he worked for one of our resellers. Very interestingly, I think the advantage of working for a reseller is the breadth of different applications that the people from either sales or technical who work for those companies get to see on a regular basis. In terms of interacting with all of you as our customers, our potential customers, and seeing what can and can't be done and seeing what you need, and working through that with the solutions offered from SOLIDWORKS. So Sashi got to learn a lot about the portfolio, about what's possible. He was a project engineer as well, so he's got a vast array of experience. He's been working with SOLIDWORKS for 2 years. And has again gotten to see a wide variety of different applications, and we love when you guys come see us and ask us, what can we do, how can we do this, please help me and show me. And this is where your reseller obviously is the first line of help for that. In often cases they will come and pull in people like Sashi to help them out and get more details. So Sashi is going to take you through the second portion of this series on plastics that we're doing, get you to the next aspect. You've got your part designed. You need to make sure that the mold that's going to design it is going to do it properly, and he's going to take you through some of that information. Michelle will be monitoring the questions as we go, and I will come at the end to give some closing words. So over to you, Sashi.
Thanks, Joelle. My name's not that difficult. So.
Oh, sorry. For French people, some names are hard. For English people, French names are hard. There's all it's linguistics, I think, at the end of the day. But I take it, if I took it slowly, I would definitely get to it and practice it 100 times. I would definitely get to it.
Well, I wanted to personally thank everyone for attending the webinar today. Like Joel said, it is a mouthful: how to analyze more cooling line layouts and predict molded part warpage using SOLIDWORKS Plastics. Yep, it is a mouthful, but I think this is a very important aspect of injection molding, and specifically the injection molding analysis, and being able to use and visualize using design validation tools like SOLIDWORKS Plastics, and being able to predict some of these potential issues early on really helps with that, with the injection molding process, as historically it's always been a little bit of a dark art, and relying on people's experience, but we're hoping to kind of shift that over and using the help of tools like SOLIDWORKS Plastics to make it much easier, and streamlining that process for plastic designers and mold makers as well. So, just one thing before I jump into the content. I know Joel mentioned you can ask questions during the presentation. I hope you will have a lot of questions. Feel free to ask them. So in your go to meeting panel, there is a questions a questions area that you can type in your questions. So just to visualize so you can see it, this is the slide in there. So let's jump right into the webinar. Let's jump right into the content. Let's kind of define what we are trying to do today, right? So if you've been through some webinars before, maybe you've seen some of the more basic setups for SOLIDWORKS Plastics. For today's webinar, we're going to be focusing on warp and cooling, and how do we validate those, and how do we predict warp, and how can we use design validation to create better cooling lines and create better cooling effects in our plastic parts. So just to define the warping, right, you can have three types of warp. Witch hat, you can see how it looks like a witch hat. You can have a chip effect, where it's warping in both two axes, and you can also have kind of a taco shape, warp shape as well. So the reason why I put shrinkage in parentheses there, because a lot of times warp and shrinkage is kind of looked at separately, but really shrinkage is a contributing factor to part warpage. So a lot of times when you run your analysis in the early stages, when you just run maybe a fill analysis to see if your part is filling up, you can already start to identify if the part is gonna start to shrink. Now, that is an early telltale sign to your part potentially warping towards the post injection molding. So if you have a lot of shrinkage early on in the process, we want to try to fix that, whether it's in the design stage or the injection molding parameters. We want to try to fix that as early as possible. So some of the contributing factors to warpage is variation of temperature as the part cools in the mold. So we are going to look at that today, right? So while the part design, thin walls, and some of your injection molding parameters can help with warping, cooling lines is a very important aspect of that. So we want to try to add cooling lines to our analysis. And if it's not fixing the warp, you can even change the cooling lines and change our cooling line, cooling line setup to try to help with that situation. Variation of pressure of the melt in the mold, and lastly, variable rates of shrinkage depending on molecular and fiber orientation. And we can actually look at a lot of these, especially the molecular and fiber orientation, again using SOLIDWORKS Plastics, and that will give you a really good idea of maybe even potentially changing your gate location so that your plastic distribution can be much more even and help with that fiber orientation as well. So the next thing we're going to look at is cooling. I know this is a lot of literature, but very important. So I decided to include this. I'll give you a couple seconds to read it yourself, and then I'll just kind of touch on this real quick. So cooling lines happens throughout the injection molding process, right? Whether or not we intend to cool the part, it's going to cool because of two reasons: natural convection with the air and forced convection, which is your cooling lines. You're not going to have injection molding setup without cooling lines. It's always going to be there, and that's going to be your forced convection. So depending on the type of coolant that you're using, your cooling line shape, your cooling line diameter, whether you're including baffles, you can help with that cooling scenario. So when we are looking at a simulation analysis of injection molding, we always have to keep in mind that the cooling starts as soon as the plastic is being injected into the mold. All right, so for today, we're going to look at this plastic part, which is it's the spool holder, which is a part of the weed cutter. So if you are like me in the East Coast, we are a couple of weeks away from good weather and a lot of grass cutting and weed cutting. So I'm looking forward to it and also not looking forward to it. But I have a weed cutter and I actually recognize this part, and I feel like a lot of people have seen one of that. So I decided to use this part. And we're going to start the analysis with filling. This is always something that needs to be done, regardless of whether you're running a cooling analysis, a warp analysis, or pack analysis. We always want to make sure that the first thing is the part is going to fill. I'll tell you right off the bat, this part will fill, but it's always good to run a sanity check to ensure that the part is cooling. The other thing that we want to look at when we are filling the mold or running a fill analysis is to, again, right, as I mentioned, check for that shrinkage early on. And we can also get some preliminary results on cooling time. So, if the cooling time is extremely high, then that prepares us for to set up a much better cooling setup for that cooling analysis. Now, during the filling, we'll be able to identify things like air traps, well lines, which is not a focus of today's webinar, but for some of you who are not familiar with SOLIDWORKS Plastics, we're able to cover all of this in that fill process. Once we are done with filling, we'll talk about, we will certainly run the pack analysis. So at this stage, the plastic is going from that liquid to solid. So it's that's why we're calling it the packing phase. A few things that we can identify during that stage is things like gate freezing, volumetric shrinkage, and insert temperature. Again, this is a very important step, again, because of that volumetric shrinkage. So if you're running an analysis, a lot of times you might just run a preliminary analysis, whether it's fill or just fill and pack. And if you're starting to see that shrinkage early on, we can fix those problems early in the design rather than having to run that entire analysis and then identify warping issues. Of course, we're going to run that warping analysis, and using the warp analysis, we'll be again able to see any type of volumetric shrinkage, which is a little bit more accurate than the results we get from the pack analysis, because it's going to take into account any residual stresses, in-mold residual stresses, and quenching thermal stresses in your part. Of course, we will be able to see how much your part is displacing. and sink marks. So again, just an added benefit to running the analysis, the injection molding analysis. So a few things that can help with warping is things like increasing packing time, increasing packing pressure, decreasing barrel temperature, decreasing cooling temperature, and increasing cooling time. So when we're approaching a plastics analysis, we always want to think of it as an iterative process. So we always start with that fill analysis. Then maybe our revision number 2 is a fill and pack analysis. And we're starting to get an idea, right? We're starting to recreate that injection molding process of injection, packing, cooling, and ejection, right? That 4 steps. So we can essentially recreate that realistic process right within SOLIDWORKS Plastics. The third step is running that warpage analysis. And typically you want to run a warpage analysis in your second or third iteration without any cooling line first, because you want to see how your part may displace without any type of cooling and only taking into account natural convection. So no forced convection at this point included within the analysis. So this will give you your maximum displacement if there's no cooling lines. Well, that's not very realistic, but that will give you some factor of safety, right? Because now you're starting to see the part in its natural state where it's going from a liquid form to a solid form. It's being ejected from the injection molding machine, and it's starting to shrink and warp. Based on those results, you can set up your cooling lines accordingly, set up your baffles, perhaps in if depending on how the part is warping, whether it's a taco shape or witch hat, we can sketch out cooling lines to ensure that areas which are displacing heavily can maybe have better cooling in those areas, or increased cooling time in those in general. All right, so cooling analysis essentially kind of ties in everything that that you're running for the analysis, right? For after you run your fill analysis, pack analysis, warp analysis, you set up that cooling analysis, it kind of ties in everything. You'll be able to identify cooling time. So depending on your cooling line shape and the flow rate, you'll be able to get an estimate cooling time. You'll be able to identify average temperature of the part at the end of cooling, heat flux in your part, and how much heat was removed, essentially, right? Because that's the whole idea is if your part is coming out of your out of the injection molding machine at X and we want it to be at Y, running the analysis we'll be able to identify that. The other thing with running cooling analysis is baffle and bubbler placement. So you can test different placements, right? So not necessarily a baffle is going to be right down the middle of a part like this, where you have a hole right down the middle. It's not necessary. A lot of times people think that, oh, that's going to be the most common area to add a baffle. Maybe not, right? So depending on how the part is warping, we can actually move that baffle or add a baffle in a different location. So with that said, let's go ahead and jump right into SOLIDWORKS. Okay. All right. So so this is the part in question that I was talking about. So this is what you call the spool cutter. You have basically that wire coming out from 2 sides here, right, on your weed cutter, and that wire spins around really fast and cuts all your weed. So this is essentially, typically it's an injection molded part, and it has some varying wall thicknesses. Of course, it has plastic part features, and I think it's a very good part to analyze. So looking at SolidWorks Plastics, so this is just a quick overview if you have not seen SolidWorks Plastics, right? So it's a SolidWorks add-in. So if you go into your SolidWorks add-in tab, you can turn on your SolidWorks tab and it will bring up your SolidWorks setup right here. And when we have our SolidWorks Plastics turned on, we'll have a tab for your SolidWorks tab right here to set up the analysis. So as of SolidWorks 2019, we now have the ability to set up a few parameters, a few injection molding parameters before you even mesh the component. Some of those parameters are your injection location, which is huge, and I'll kind of talk about that in a second here. Your control valve, so if you have any control valves in your injection molding machine, you can add those, and your mold wall temperature. So mold wall temperature, you can add that as a parameter, or you can even add a virtual mold to your analysis, or you can actually even add an actual mold to your analysis and run the analysis and let the software calculate the convection and the conduction that's going on. Okay, so just to kind of show you how this works, injection location. This is slightly different from what you might have seen before, where injection location had to be placed after the part is meshed. So what's nice about having this as an option before meshing, we can actually model in the gate size. So these faces right here, these features that were just modeled into SolidWorks, is essentially the gate location and the gate size. So when we select as part of this parameter setup, so it makes it very, very easy. Of course, you can set up multiple gate locations. That's always been a feature with SolidWorks Plastics. So I'm going to hit the green check mark, and you can see that I'm all set with my injection location. So like I mentioned, you can also include a control valve. So if selecting anywhere, selecting on a face like this, you can see that it includes a control valve in that location. And of course, you can also set up a mold wall temperature. So once you have your injection location, the next step is to mesh the part. So I'm not going to spend too much time on that. So I'm going to just switch over to my configuration of my meshed component. And we'll spend a couple minutes just setting this up, setting the fill, pack, and warp analysis, like I said earlier, as a sanity check, right, to begin with. So once we've meshed the part, of course, we want to set up the material. So for this analysis, we're just going to use a generic material. So again, for some of you who are new to SolidWorks Plastics, have never seen this, this is our SolidWorks Plastics database. We have over 5,000 plastic material in here, and more to come. And we've just gotten some confirmation from many plastic companies that are creating the polymers that they're going to be providing us with more material, which are brand new. So a few thousand more are going to be added, and you can also add your own material, so you can create your own custom material as well. So the next thing we want to look at is our fill setting. So like I said, I don't want to spend too much time on this. It really is for a sanity check. So I'm going to keep all the default conditions as is. For my pack analysis, same thing. You can set up your pure cooling time. If you have a a target cooling time, you can add this, and it will tell you if it's within that time range. And for your warp analysis, you can specify the ambient temperature when the part is ejected, and specify the gravity, so how the part is being ejected from the injection molding machine. So this Y is based on this. So if you look here, it will look something like this. Let me see here. So if the part is going to be ejected like this, so this is in the downward Y direction. So you can just specify that for your warp analysis. So warp analysis is really very, very simple. I mean, really the most important criteria here is the ambient temperature, because it's trying to calculate the temperature that the part comes out of the injection molding machine and how much time it has to cool down to that 30 Celsius. And it will calculate all the residual stresses that's building up in the component and how it's displacing due to that, all those stresses that's induced within that plastic part. Let me just go ahead and hit that green check mark. So you can see we have all the green check mark. In terms of boundary condition, I'm not going to set anything up for this specific analysis, but just so you know, there's quite a bit of information that you can input as part of the analysis. The way this works with design validation is you have the minimum requirement to run the analysis. So the minimum requirement to run a fill pack warp analysis is your process parameters, your material, and your mesh, and of course your injection location. Once you have all of this, you'll be able to run your flow pack warp analysis. The boundary conditions here are added information to increase the accuracy of your results. So if you know things like perhaps the clamp force, or if you have any runner elements, if you have any air vents, you can add this information and your accuracy goes much higher, right? So for example, when you run the analysis and let's say your results is within 10% of what you're seeing in real life, that's great. You can make quite a bit of engineering decisions based on that results. But if you like to get maybe even closer, maybe 8% or 5% to actual real world results, then adding more boundary conditions will get you closer to those final results. So at this point, we are ready to run that sanity check just to see how the part will fill, how it will pack, and of course, if it will have any warp. And you can do that by simply just right-clicking the flow pack warp analysis and hit run. So of course, for time's sake, I've already ran this, and we'll take a look at some of that results here. And let's see results. So of course, like I mentioned, the part does fill up without any issues, but just so you can see it, how it fills evenly. And I think what we are most interested in here is the warp analysis. So based on just the two parameters that you had set, which is I'm just going to go ahead and hide that, which is the ambient temperature and the ejection direction, we can get quite a bit of results. So here you can see total stress displacement, and we can identify the displacement in the X direction, Y direction, and Z direction, and of course total. So the color here correlates with how much that part is displacing, right? And based on this, kind of looks like we have maybe a taco shape. Well, not so much, because this is in the two directions. Taco would be all four. But we can start to see how this part is displacing. Now, 0.3 millimeters is not very, very clear. So if you would like to see how the part is displacing, you can actually increase the deformation scale. So here, you can see as I increase the deformation scale, we can start to get an idea of how the part is deforming. And we can also animate the deformation. So you can see this is how, of course, exaggerated, this is how the part will be warping and shrinking after it's ejected from the injection molding machine. So here are other results that we can extract from the warp analysis. So in-mold residual stresses, quenching thermal stress, sink mark profile. If this part is a highly visible part, cosmetic part, we want to try to reduce sink mark as much as possible. In-mold residual von Mises stresses and demold residual von Mises stresses. So the combination of all these different stresses is what's really causing that total stress displacement. And cooling and setting up that cooling line can really help with that displacement. So that will bring us to our next section for this webinar, is how to set up those cooling lines. So for that, I'm going to move to my next configuration here, which is an extension of the fill pack warp analysis. So that fill pack warp analysis. And to set up your cooling lines, you would have to remesh the component. And you have the ability to add running and cooling system designs. And you can also create a virtual mold generation. So for this part, I didn't include a mold, which you could have just modeled up in SolidWorks. And if you would like to include the conduction from a mold, you can include a virtual mold generation. So I'm going to skip that because we want to try to focus on just the cooling lines. So I'm going to hit next here. And this brings us to our channel design. So to create cooling lines, you will need sketch lines. So let me go ahead and turn those on. So sketch lines can be created simply within SolidWorks using your sketch tools. And here I have some sketch lines that I've created, and I've suppressed them. So I'm just going to unsuppress these sketch lines. And you can see these sketch lines represent my cooling lines. So going back into my plastics analysis. Cooling channel. And to create the cooling line, it's very easy. All you need to do is just select the sketch line. So there's two ways you can do that. You can hold on your control key and simply just select all the sketch lines. A much easier way to do this is to, you could right click any sketch line. You can just say select chain. And here is where you specify what the diameter of the cooling line is. So I'm just going to use the default condition right now. So it's going to be 10 millimeters. And I will say assign, and you can see it creates that cooling line for me. So again, if I just right click this and say select chain and say assign, it creates that cooling line for me. So it's very, very easy to create. So I'm going to continue to do that here. So I'm just holding down Control and selecting Select Chain, so I can do it all in one go. There you go. And as you can see, I purposely did not set up that last cooling line. Now, the reason why is because this line going right down the middle is a baffler. So to set that up, select the sketch line. And right here on the channel parameters, you can select whether this is a baffle or a bubbler. So here I will set this up as a baffle, and I will assign it. And you can see that it's represented as a different color. To move along here, I'm going to turn this back into general and say assign, say next, and it creates my cooling channel for me. So at this point, you have essentially meshed the cooling lines, and the solid mesh is requesting that you continue with the meshing process, and you mesh the cavity, which is the plastic part, and if you have a virtual mold, you will also mesh that. And again, right, because of time, we don't want to spend too much time on that. So assuming that we already have our cooling lines in place, let's take a look at a cool fill pack warp analysis. And I'll show you how to set up your coolant that goes through your cooling line. So here's the cooling line that's meshed and completed. And if you go into our plastics analysis, under material, first of all, you have now your coolant option here. And for coolant, we have 39 different coolants that you can pick from. And again, like I said, you can set up your own if you don't find one on this list. But in most instances, I've seen pretty much every coolant on the market is on this list. So for this analysis, we simply use water. And the next parameter that we have is under our boundary condition, essentially to set up the direction of as the water is flowing through this, and as well as your inlet temperature and flow rate. So once you have meshed the coolant, the cooling lines, and you open up your cool pipe boundary condition, it will automatically state all the different cooling lines here. Now, depending on the direction, you can specify which direction is the inlet and which direction is the outlet. So for example, for this part right here, let's say if I want to switch the inlet and outlet, all I need to do is just say reverse flow, and you can see that it switched the flow and it made this point as the inlet. So it's actually very simple, very intuitive. Any SOLIDWORKS user should be able to set this up without any issues. So I'm just going to reverse that back because I want this to go in the opposite direction. And you can also set up your flow rate. So flow rate is independent of every cooling line. So you can set up different flow rates if you need to. And you can do that right here. And as you click through all these different cooling lines, you can set up all the different the flow rates. So cooling line setup, very simple. You can also change your coolant from right here if you need to. And once you have your coolant and your cool pipe set up, that really is the minimum requirement to be able to run this analysis to view how that cooling analysis will affect the results. So let's take a look at, we'll start with the cool results. Very cool results. And we can look at how it's affected the warping. So here we can see it will right away. It will tell you the part cooling time, so how long it will take to cool. So 19 seconds, right? So depending on your injection molding criteria, right? How many parts you need to injection mold in your injection mold run? how many times a day it's running. That goes down to the second, right? So if this is even 1 or 2 seconds too long, then you need to perhaps change the coolant, add more cooling lines, right? So many different things that can be done. The whole idea to this tool is that it helps you make those decisions, right? So you can, before even running the analysis, before cutting the mold, you can already start to make some of these engineering decisions based on these results. So cooling average temperature. So we can see at the end of cool, what is the average temperature. So of course, right, that ambient temperature was 30. So the majority of the part is at around 30. And we have some areas which is still heated at the end of that cooling analysis. Temperature at end of cooling. You can see that here as well. And few other things. We didn't add a mold, but if you did add a mold as part of your analysis or a virtual mold, you can even get some of that information. What is the mold temperature at the end of the cycle? So very, very useful results to make very important decisions. So the thing about SOLIDWORKS Plastics is all these results depend on each other and they feed into each other. So the cool analysis, if it is included as part of the SOLIDWORKS Plastics full run analysis, it will essentially start the cooling as soon as the part starts to fill. So if you have a cooling analysis, your flow analysis will start to change. Your pack analysis will start to change. Your pack analysis results, flow analysis results will start to change. And of course, your warp analysis will also change. So looking at the warp analysis, we can see that the warp has certainly changed. Than from what we had before. You can see that this time around, it's warping in a little bit in a different shape. So adding that cooling gives you a much better perspective of what is going on with your part and how it will really warp with that cooling lines. So being that SOLIDWORKS Plastics is 100% integrated into your design space, you can make changes to your plastic part design and rerun the analysis and get all your updated results very easily. In addition to that, and you can use configurations to do that. So let's say if I have plastic part design 1, plastic part design 2, let's say if I have a thicker wall, all I need to do is just rerun the analysis for that different design. Configuration can also be used for different injection molding setup. So let's say, based on the results, I want to change my cooling line design. So I have a configuration here with a different cooling line design, and this can also be a discussion tool, right? So if you're part of an engineering team and you want to test different cooling lines and perhaps discuss it, you can have it all as part of one file set. So this is just one SLD PRT file, and you can have multiple cooling lines and you can compare the different results that you get from the analysis. So looking at this, you can see that I've changed my cooling line design a little bit. I've moved the baffle out of that inner circle to this area right here. And just rerunning that analysis, we can take a look at that cool results. Maybe see if we can change that cooling time. The cooling time is still about the same. Well, essentially the cooling lines is the same design. And we can see the temperature at the end of the cool as well. And you can see this area right here, this area is specific to where we add the baffler. it's a little bit closer to ambient temperature versus this side right here. So that kind of concludes the cooling line design. If you have any questions, specific questions, feel free to type it in, and I'll be happy to answer. But before I wrap this up, oops. I wanted to kind of give you a perspective of what we looked at today. So SOLIDWORKS Plastics comes in 3 levels: Plastic, Standard, Professional, and Premium. And the way we've laid out this, the tool is based on the injection molding process. So the fill process is really, the fill and pack is included as part of that plastic standard. And if you need a little bit more as part of your analysis, for example, if it's multi-cavity, if you have runners and if you need to balance runners. So imagine if you had a plastic cover and you wanted to injection mold the cover, which is different geometry, as part of the same family molds, you can run a runner balancing so that the polymer is spread out evenly. You can have co-injection, shrinkage analysis, insert and overmolding, and report analysis as well. And I'm going to show you that right before I conclude this webinar. And last but not least, I think one of the most important aspects of injection molding is being able to predict warp. And let's face it, right? 99% of the time when you run injection molding, you're going to have warping. And it's important to identify warping and add in your cooling lines, which comes as part of that plastic premium and that warp analysis. Adding cooling lines helps you predict how the part will warp if you had different cooling line setups. So one last thing before I hand this off back to Joelle. For warp analysis, I know a lot of times people talk about possibly running windage, which is cutting the molds in the anti-warp direction so that the part warps into the intended direction. This is also included as part of SOLIDWORKS Plastics. So we have an export tool here that lets you export the part as an STL. And you can export this part as a anti-warp, which helps you with that windage analysis as well. So I just wanted to throw that in there. And one last thing, running this this analysis, we can also create reports. So here we have a report which was created as part of the analysis, and this was created in a PowerPoint format, and you could also create this as a PDF format. So this is a one-click reporting tool included as part of SOLIDWORKS Plastics. So you can see it includes all the cool warp, flow results, pack results, cool results. If there's any, it will all be included in here. So this is a very nifty tool, again, just for that, like I mentioned, that discussion, being able to share those results with other team members makes it much easier. So with that said, I just wanted to wrap this up and give it back to Joelle. Thank you very much.
Well, thank you, Sashi. That was great information, as always, when you do live or webinar events with us. So thank you so much. Were there any questions, Michelle, that came up during the webinar?
No questions came up.
No questions came up, so everything was crystal clear. We appreciate that. So as mentioned, the webinar that we did last week, which was part 1, how to design your parts properly the first time and optimized for for doing everything properly and saving time and money, obviously, is recorded. If you go to our channel here, you will see the one from last week. You will see the one from today, and many other webinars that we've hosted along the weeks and the months and the years. So there's a lot of good information there. And of course, there will be a contact at some point from your reseller just to see if there's anything that you have or thought about since that were not answered. We know that as you mull this information over, you come up with new things. And if there's other people you want to share this with, you can also share either the link that you got to join the call. That works as well. They just have to register and they'll see the recorded webinar. Or go to our channel. So lots of different options. If you have any questions, you're more than welcome to reach out to any of us directly as well. We'd be happy to work with you and answer your questions. We want to make sure that there's a path to making the right decisions for your company and your application. So let's work together on doing that. So once again, thank you all for joining us. Thank you, Sashi, for joining us to share this info. And we'll see you on our next webinars in April, hopefully. Have a great day, everyone. Bye.
Thank you. Bye.